How do lasers work? The science behind concentrated light. Lasers are everywhere in modern life. They scan supermarket barcodes, carry data through fiber optic cables, enable delicate eye surgery, and measure the distance to the moon. Despite their ubiquity, lasers often feel mysterious, beams of perfectly straight, intensely focused light that seem almost unreal. Yet the principles behind lasers are firmly rooted in quantum physics and a clever manipulation of how atoms behave. The word laser is an acronym: light amplification by stimulated emission of radiation. This phrase points directly to the key process that makes lasers different from ordinary light sources such as bulbs or the sun. In everyday light, atoms emit photons randomly, producing light that spreads out in all directions and contains many wavelengths. Laser light, by contrast, is highly ordered. Everything begins at the atomic level. Atoms contain electrons that can occupy specific energy levels. When an atom absorbs energy, supplied by electricity, another light source, or a chemical reaction, its electrons can jump to higher energy states. This excited state is unstable, and the electron eventually falls back to a lower level, releasing energy in the form of a photon. This process, known as spontaneous emission, occurs in all light-emitting materials. Lasers rely instead on stimulated emission, a phenomenon predicted by Albert Einstein in 1917. If an excited atom encounters a photon with exactly the right energy, it can be stimulated to release a second photon that is perfectly matched to the first. The two photons travel in the same direction, have the same wavelength, and remain in phase. This precise duplication is what gives laser light its remarkable coherence. To make this process useful, lasers employ a gain medium, a material such as a crystal, gas, or semiconductor, placed between two mirrors. One mirror is fully reflective, while the other allows a small amount of light to escape. Energy is pumped into the gain medium, creating a population of excited atoms. As photons bounce back and forth between the mirrors, stimulated emission multiplies them, amplifying the light. When enough amplification occurs, a narrow, powerful beam emerges through the partially reflective mirror. This structure explains the defining properties of lasers. Laser beams are monochromatic, meaning they consist of a single wavelength. They are also highly directional, spreading very little over long distances. Perhaps most importantly, they are coherent, with waves that move in step, an essential feature for applications requiring extreme precision. Different types of lasers are designed for different tasks. Medical lasers cut or reshape tissue with minimal damage, industrial lasers slice through metal, and low-power lasers read data or align instruments. Though their purposes vary, all lasers operate on the same fundamental principle: controlling light by controlling matter at the smallest scales. In essence, lasers work by turning the chaotic behavior of atoms into disciplined light. What looks like a simple beam is, in fact, a triumph of quantum physics, made practical, reliable, and indispensable to modern technology.